So today we're going to discuss examples of distributions, specifically discrete distributions, that all these distributions that we're discussing are examples of what we would call parametric models in statistics, that a parametric model / distribution family is something that has a specific form but can change according to a fixed number of parameters, like binomial distribution that we've discussed a bit in the past and that we'll be discussing more shortly. It's anytime you have repeated trials with some given number of success, you can model it using a binomial distribution. And the advantage of these particular distribution families is they're a simpler way to model a population. You can use them in common situations with similar mechanisms. Binomial, once again, when you have a trial that you're repeating a fixed number of times, and the nature of this trial can be just about anything. And the thing that's nice about this is that it becomes really easy to work with and make inferences about whatever it is that you want to make inferences about. Say a binomial distribution, for instance, you have a coin, you want to know if it's weighted, something like that, or you want to, what's something else you could do with a binomial distribution? You want to know if, or compare the probability of success in two binomial distributions, things like that. All you have to do is estimate the probability of success P for your binomial distribution, and you know everything about the distribution, which makes it really easy to do the math and the other inference that you want to work with. If you've taken a number of statistics classes in the past, you may have heard of this idea of non-parametric inference, where you don't want to assume that your data follows any specific distribution. And you can do inference in that setting, but these models can be a lot uglier than what you would get with a standard parametric model. So in this class, we emphasize parametric models both because they tend to be the most commonly used in practice, and they're also the easiest to come up with mathematical properties about, which is kind of a focus of what we do in this class. So anyway, simplest example of a discrete distribution is a discrete uniform distribution, where you have some finite number of possible outcomes, and your discrete random variable is equally likely to be any one of those outcomes. So your sample space in general would be 1, 2, up to n. Obviously, there's a one-to-one mapping between any other finite sample space, and that sample space, you can take that particular sample space without loss of generality. And very easy to show, the probability mass function is just 1 over n because all of the outcomes are equally likely. And CDF, also easy to show, it's just x divided by n. And if you work through a little math that I won't show, you can find that the expected value is n plus 1 over 2. And if you wanted, you could define a discrete uniform distribution on arbitrary numbers n0 up to n1 with the probability mass function listed below. In general, there's not much reason to do that because there's a one-to-one correspondence with 1 to n, as I just said. More commonly used distribution is the binomial distribution, which, to explain the binomial distribution, we'll first look at a simpler form of the binomial distribution, which is the Bernoulli distribution, which is where you do a single trial of an example where the outcomes are binary. By convention, you call these outcomes success or failure, and the probability of success is p. And there's a number of ways that you could do this. I mean, coin tossing is kind of the canonical example. You call heads a success and tails a failure, or something like that. Or you could do something like roll a die and say that an even number is a success, an odd number is a failure, or you could say that you do a telephone interview, ask them which candidate they're going to vote for. Candidate 1 is a success, candidate 2 is a failure, whatever the case may be. So if you define a random variable y to have value 1 if the outcome is a success and 0 if it's a failure, then y has a Bernoulli distribution. The sample space here is obviously just 0 and 1. Probability mass function is equal to 1 with probability p and 0 with probability 1 minus p. And which you can write for the PMF as p to the y times 1 minus p to the 1 minus y, because as you can see, if y is equal to 1, then the 1 minus p term will have exponent 0, and if y is equal to 0, then the p term will have coefficient 0, will have exponent 0, so you end up with just probability y equals 1 is p and y equals 0 is 1 minus p. And if you want, it's also relatively straightforward to calculate the CDF, mean, and variance. So now let's say that we do a series of n Bernoulli trials where each trial is independent of the other trials, and the probability of success or failure is the same for each trial. That for the ith trial, the probability of success is p, and the probability of failure is 1 minus p. This probability does not change over the various trials. The other way you can describe this, say you have n independent identically distributed Bernoulli random variables. Oftentimes in the statistical world, when we talk about independent and identically distributed, we say IID for short. Then if you simply take the total number of successes over the n trials, then that's said to have a binomial distribution, where it's just the sum of n Bernoulli random variables, or equivalently, you just count the number of successes over the total of n trials. So, simple example of a binomial distribution, say you toss 3 weighted coins where the probability of heads is p and the probability of tails is q. So then probability of 3 heads, of course, is p cubed. The probability of 3 tails is q cubed. Likewise, 2 tails, or a head and a tail and 2 heads is p squared times q. Probability of head and 2 tails is p times q squared, etc., etc. And like I said, the binomial distribution is focusing on the number of heads, or more generally, the number of successes. That here we see that the probability of getting 0 heads is going to be q cubed. Probability of getting 1 head is going to be 3 times pq squared, because there's 3 different ways that you can get 2 heads and a tail, namely tails, heads, 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 tails, heads, 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 tails. Each of those p squared times q. Similarly, there's 3 outcomes that can give you, like I said, it's back, where there's 3 outcomes that give you a head and 2 tails. 3 times p times q squared, and only 1 outcome of 3 tails, which has probability q cubed. So, to generalize this, any particular sequence where you have s successes and n minus s failures, that the probability of that is going to be p to the s times q to the n minus s. However, if you remember from the combinatorics lectures, that there's the number of different orders where you can get s successes from n trials is going to be n choose s. So that implies that the total probability is going to be n choose s times p to the s times q to the n minus s. I'll show here in a second. So formally, binomial distribution will have sample space from 0 to n. Probability mass functions, I just said, will be n choose s, the number of different possible orderings for s successes in n trials, times the probability of getting s successes, p to the s, times the probability of getting n minus s failures, which is q to the n minus s. And it's easy to show that this PMF sums to 1 using the binomial theorem. I think I may have proved this in an earlier lecture, but otherwise, if you just take the binomial theorem, let A equals P and B equals Q, then you'll end up with 1 equals precisely the expression that I have up there. And there is no simple form for the CDF. You simply have to take the sum of all the individual PMFs going from 0 up to whatever value of y that you're interested in. If you need to compute this in practice, your best bet is to probably use R, some other statistical computing package that has a function to compute this built in. And so in general, if f of y is going to be 0 if y is less than 0, since the smallest possible value for the binomial distribution is 0, probability that y is less than or equal to 0 is equal to the probability that y is exactly equal to 0, which is of course q to the n. Probability that y is less than or equal to 1 is the probability of getting 0 or 1 success, which is of course q to the n plus n times p q to the n minus 1. Likewise for f of 2, etc., etc. In practice, as I said, you'll probably want to do this using R or something like that, because calculating it by hand would be tedious. So, simple example of a binomial distribution. Say a physician treats 10 people having a particular disease, and the probability that the treatment's successful is 1 out of 4. So what's the probability that exactly S people have successful treatments? Well, the formula would just be 10 choose S times P to the S times Q to the 10 minus S. So if you compute that, the probability that no people get successful treatments would be 0.056. The probability that 1 gets successful treatment is 0.188, 2 is 0.282, etc., etc. Hopefully straightforward enough. Any questions about the binomial distribution before I move on to the Poisson? Okay. Poisson distribution was derived as kind of a limiting version of the binomial distribution, is one way to think about it. That say that you have a binomial distribution, but the number of trials becomes very large, but the probability of success is very small, so that n times p stays roughly constant, equal to a value lambda. Usually the way you will think of this lambda is it's often called a rate parameter. You could think of it as the rate of people that develops a rare disease, say like cancer or something, that the probability that any given person develops cancer is very small, but the population of all the people in the country or the world who could develop cancer is very large, and the number of people times the probability of developing it would be your rate parameter, the approximate rate at which people develop cancer. And you can show that if n times p approaches some fixed value lambda as n gets large, then this limit is precisely e to the minus lambda times lambda to the y over y factorial. And quick proof of this here, that the PMF for binomial distribution is just what I've written down there. So if we're operating on the assumption that lambda equals np, then we can write that as n factorial, n choose y times lambda over n to the y power times 1 minus lambda over n to the n minus y power, which that can be rewritten as lambda to the y over y factorial times 1 minus lambda over n to the nth power times 1 minus lambda over n to the minus y power, n times n minus y plus 1, multiplying up to n divided by n to the y. Now, as n goes to infinity, that piece there is going to 1, as is this piece here getting closer and closer to 1. So you end up with lambda to the y over y factorial times 1 minus lambda over n to the n power. The limit of that, of course, is just e to the minus lambda, so we end up with e to the minus lambda times lambda to the y over y factorial, which was precisely what we wanted to show. So just to show that this works in practice, here n and p aren't even that large, but we say we have a binomial with 5 trials and probability of success 5 versus a Poisson with rate parameter 1. And even for n and p fairly modest, you see that the Poisson probabilities are fairly close to the binomial probabilities. Since Poisson represents rates, there's no upper limit to the Poisson distribution, unlike the binomial. The binomial, if you're doing 5 trials, the probability of getting 6 or more successes is obviously 0. For Poisson, you can have an arbitrary number of successes. The probability of 6 or more is 0.001, close to 0, but not exactly equal to 0 here. And just as an example of a type of argument that will prove to be useful later in this class, another way that you can prove the convergence of the binomial to the Poisson is via the convergence of the characteristic function. As you'll recall from a couple weeks ago, the characteristic function of the binomial distribution is p times e to the it plus 1 minus p to the nth power. So again, we let p equals lambda over n and rewrite the characteristic function using that lambda over n parameterization, and we end up with, and after simplifying the algebra, we end up with this expression here, 1 plus lambda e to the it minus 1 over n. And as n goes to infinity, that converges to e to the lambda times e to the minus it minus 1, which is precisely the characteristic function of the Poisson distribution. And in general, if you can show that for a given sequence of distributions, if their characteristic functions converge to the characteristic function of another distribution, that implies that those distributions are converging to whatever distribution that was. So in this case, that says that if n gets large for the binomial distribution and n times p is equal to lambda for large n, then the binomial distribution is converging to the Poisson distribution. So, example of the Poisson distribution, that say the death rate among females aged 15 to 44 from pulmonary embolism is 4 per million. So if you have a city of 1 million females in that age range, then the rate parameter would be approximately 4. So, as I said, that can be written as just the probability for a given woman to develop pulmonary embolism times the number of women in the city. And if you compute those probabilities, we see the probability of 0 cases is approximately 0.018, the probability of 1 case is 0.07, etc., etc. So here's some examples of when you would use the Poisson distribution in real life. rare events, incidents of rare diseases, for instance, often used for like failure of equipment and things like that. Some of the more interesting modern applications that are actually active research areas in statistics these days is you can use it to model the pixel intensity for certain types of image processing examples, which I don't know that much about, but I do know a little bit about this idea of reading some molecular binding experiments. If any of you have any kind of background in biology and know about RNA-seq technology, which is basically RNA sequencing to determine how abundant certain RNA transcripts are in cells, it's often modeled using a Poisson distribution, and I don't really know the details of this, and it's way beyond the scope of this class, but if you're ever interested in writing a dissertation on that type of thing, you may get to use the Poisson distribution, so it does have some function other than to make your life more stressful around exam time. Anyway, any questions about the Poisson distribution? Okay. On to the hypergeometric distribution. I know when Mike Wu used to teach this class, he apparently would go off on rants about how much he hates this distribution, and I will admit it's always confused me as well, so I'll do my best to give the motivation for what's going on. It's just, to me, like binomial, Poisson, negative binomial are all very intuitive, but every time I use the hypergeometric distribution, I have to like think about what's actually going on here. So, kind of the canonical example for why would you ever care about the hypergeometric distribution is what's known as the capture-recapture method, that say you want to estimate how many fish there are in a lake. So you do something like this. You catch like 100 fish, put a tag on them, throw them back in the lake. So wait a while for them to intermix with the rest of the population of the lake, and then catch a new batch of, say, 120 new fish, and see how many of these new fish have tags on them. And then you find that like 10 of them are tags. So the hope is that the proportion that were marked when the proportion of the tagged fish that were recaptured should be approximately the same proportion of those who were not recaptured. So you can estimate the total number of fish in the lake by solving this proportion here. I didn't actually work it out, but that can give you an estimate of the number of fish in the lake. But say you wanted to come up with a confidence interval for the number of fish in the lake or something like that. Well, you'd need to know something about the expected distribution of the number of fish that you recapture under this approach, and to estimate that distribution, you can use the hypergeometric distribution. My understanding is that ecologists and people who actually study these wildlife populations actually do approximately this to estimate the size of wildlife populations in many situations. So this isn't just some crazy artificial example that we cooked up for statistics class. My understanding this actually gets used. I mean, I've never done anything with this personally, but one way or another, you can get your confidence interval using the hypergeometric distribution. So, in general, the situation where you would use the hypergeometric distribution is, say that you have a population of size big N, and it's made up of two types, where M's the first type and N minus M of the second type. So the example I just gave, you can think of there are M tagged fish in this population of size N, and so that implies there's N minus N untagged fish. So say we take a sample of size K, and we want to know the distribution of the number of tagged fish in the sample. Well, if you do all the combinatorics, that works out to be this messy thing right here for the density function. And I'll see if I can explain this without making a fool out of myself. I mean, the denominator is fairly straightforward. That we have a sample of size n, we're choosing k of them without replacement. There's n choose k different ways that we can choose these k fish. So how many different ways can you get exactly x tagged fish? Well, there's a total of m tagged fish in the lake, so the number of different ways that you can choose x of these tagged fish is m choose x, and there's n minus m tagged fish. If you choose x tagged fish, you have to choose k minus x untagged fish. So the total number of ways that you can choose k minus x untagged fish will just be n minus m choose k minus x. Multiply those together to get the total number of ways that you can choose exactly x tagged fish. Divide by the total number of ways that you can choose k fish. Wow, I explained that a lot better than I thought I was going to be able to. So, obviously, this is only defined if x is in the range between 0 and m minus n plus k up to m and k. That's just because for every one of these combinations here, the number at the bottom has to be less than or equal to the number at the top. If you have x bigger than m or x bigger than k, well, and they also have to be bigger than 0. If it's outside the range that we've listed there, then the probability is 0. Oh, oftentimes the oftentimes the sample size is going to be less than the number of tagged items, in which case it becomes simpler, and the x just ranges, and your x can just range between 0 and your sample size. So, to compute the moments of this thing, I mean, I'll walk through this example just because it's a nice illustration of some of the algebraic tricks you can use to compute complicated moments generally. That, say we want to find the expected value of the hypergeometric distribution. Well, by definition, that's just going to be x times the sum from x equals 0 to k of x times the probability of drawing that particular x, which of course is given by the PMF of the distribution. Well, for x equals 0, this term is going to be 0, so we can drop that from the sum and just sum from 1 to k. And to simplify this expression, you can use the fact that x times m choose x, if you expand out the factorials, x over x factorial, the x cancels with the x and the x factorial. We're left with the x minus 1 factorial. Similarly, you can pull an m out of the m minus 1 factorial. And this expression is just m minus 1 choose x minus 1. So anytime we have x times m choose x, we can just write that as m times m minus 1 choose x minus 1. Or you could also write that m choose x is equal to m divided by x times n minus 1 choose x minus 1. So if we do that for this expression up here, we can change this. We pull stuff out of both the numerator and the denominator. Write this is m over x. Write this down here as n over k. The x in the denominator of this cancels with the x up here. We get m over n minus k times n minus 1 choose x minus 1 over n minus 1 choose k minus 1 times n minus m choose k minus 1 minus x minus 1, which, if we pull the m over n over k out of the summation sign, we just end up with summing over all the possible values of a hypergeometric distribution where there's m-1 tag things in a population of size n-1. And so we end up with the expected value being equal to m over n over k, or in other words, m times k over n. Does that make sense, more or less? I probably should have shown more steps, but I didn't want to waste a second slide on this. Well, this isn't like a critical point anyway, but if you have questions about it, feel free to ask. So, example of when you might want to use a hypergeometric distribution. Say that vaccines are manufactured in batches of size n. You choose n vials, and if no vials are defective, then you accept that particular batch of vaccines. So what's the probability that a batch with m defective vials is accepted? Well, and I guess I probably should have written more stuff on this slide. The idea here is we would have a sample of size n, of which m are quote-unquote tagged. In this case, they're defective. We sample little n of them, and we sample little n of them to find the probability that none of them are defective. We can just say what's the probability of getting 0 tagged items under a hypergeometric distribution. And I should have put all that on the slide. I'm not sure why I didn't. I was doing this late at night. But one example that I do show here is that if we think of big N being very large compared with little n, then you can think of this as sampling with replacement, which is essentially the scenario you would have under the binomial distribution. That say that we're sampling from a really huge population and we're taking a relatively modest sample. So if you take tagged things out of the sample, it doesn't really change your probability of getting a tagged thing all that much. I'm trying to think of a good example of this. Say it's a population of 1 million, if the population of the entire state of North Carolina, and your sample is, and you want to see how many registered voters you get when you grab a certain number of people on the street. Given that a very high percentage of the population is already registered voters, the fact that you're not sampling with replacement and you already grabbed like 3 or 4 people, that is not going to appreciably change the probability that the next person is a registered voter. You can just assume that the probability that the person you grab is a registered voter is more or less fixed. Instead of messing with the hypergeometric distribution, you could model it using the binomial distribution, where you just say, let's pretend that if we grab 300 people, the probability of being a registered voter is 70%, who knows what it is. And we'll just model it as a binomial distribution with probability of success 0.7. And the next couple slides I'm going to show why this would be considered legitimate. Oh, here is a couple, I'm not 100% sure what this table is supposed to represent. I think it's supposed to be the binomial approximation of the hypergeometric that I just described, but like I said, I got these slides from Mike Wu, and I'm not entirely sure what he did with that. I should prepare better next time, but anyway. The more important point here is now we're going to show that the limiting form of the hypergeometric probability mass function is just the binomial probability mass function. I guess I should probably change PDF to PMF in this slide just to be consistent with the notation that I've used elsewhere, although PMF and PDF are often used interchangeably for discrete distributions. So let's write out the expression for this probability in terms of the factorials. It's this big, ugly, funky factorial thing. And then we can rearrange the terms a little bit that in particular, I looked at this last night and it all made sense. Now I'm trying to remember where that n factorial. Oh, I remember where the n factorial came from. It came from down there. So we pulled this n factorial up to the numerator of the numerator, and then we just kind of rearranged all the other terms up here. Now have n factorial over s factorial over n minus s factorial times m factorial over n minus s factorial times n minus m factorial over n minus m minus n plus s factorial. So now we notice a couple things about these expressions, that m factorial over m minus s factorial is just going to be the product of all the numbers up through m minus s plus 1 times m minus s factorial, which of course will cancel with the denominator, and that if you pull an m out of everything, that will end up being m to the s power times 1 minus 1 over m times 1 minus 2 over n, up to 1 minus s minus 1 over n. Similarly, we can show that n factorial, big N factorial for big N minus little n factorial, big N power times 1 minus 1 over m, etc., using exactly the same logic as above. And once again, using analogous logic, we can get that n minus m factorial over n minus m minus, in parentheses, little n minus s, big N minus m to the n minus s times all this stuff. Hopefully you see the pattern by now. At any rate, so now we let the sample size go to infinity. The population state of North Carolina is large. We also let the number of registered voters go to infinity because that's large as well, but we assume that as both of these things are getting large, the proportion of tagged items, that is the proportion of registered voters, goes to some constant. Then the probability that we get exactly S registered voters is that expression, which is going to be based on the equation from the previous slide that I probably should have written again. That's going to be n choose S times m to the s times n minus m to the n minus s over n to the nth power, which of course can be written as n choose s times m over n to the s times 1 minus m over n to the n minus s power, which of course is just the probability mass function for the binomial distribution, indicating that as the number, as the population size and the number of tagged items both get large, the hypergeometric distribution approaches the binomial distribution. So to summarize all these approximations in general, if you have a hypergeometric distribution where you're basically sampling from some population with replacement and want to see how many tagged items you sample, if you assume that both your population size and your number of tagged items are large and the proportion of tagged items is equal to whatever, you can approximate that with the binomial distribution. And if you have a binomial distribution, if you assume that your sample size is getting large and the probability of any particular item being a success is getting small, such that the rate of successes remains constant, i.e. n times p remains constant, then you can approximate the binomial with the Poisson. And that's all I've got for today. Any questions about any of this? Okay, Thursday, I'm not really going to prepare anything, so come prepared with questions because I'll be busy grading and grant writing and stuff.
Sean, I don't have